Hi, welcome to BC Video 9.7a Part 2, Polynomial Approximations of Functions. Okay, so here's what the book is going to say. So the video notes begin here. Section 9.7, Taylor Polynomials and Approximations. So first of all, whenever you have a graph and you've drawn the tangent line to that graph at a point, in the little neighborhood near the point of tangency, you're going to notice that the graph of the function and the graph of the tangent line, when you're really near the point of tangency, are almost indistinguishable. So we're saying that it's centered at or about that x-coordinate of that point of tangency. So the tangent line to f of x at the point c f of c is, in this case, a polynomial of degree 1. It's a line, right, which would make it up, we'll call it p of x for polynomial equals mx plus b because it's a line, and of course that slope is f prime of c. Now, we already have that this point C f of c is the same thing as the point C p of c because it's the point of tangency. It lies on the curve and on the tangent line. What we'd like to have is we'd like to have the slopes of our polynomial and our function be the same. So what happens now, find a first degree linear polynomial function which approximates the function y equals e to the x at a point near x equals 0. So as you will find out later, when it's near 0 or about 0, it's what's called a Maclaurin's polynomial. All right, so our P1 of x, which was a first degree polynomial, is that y equals mx plus b, right? So mx plus b. We're going to switch that order because we're going to have, since it's going to be an infinite polynomial eventually, it makes sense to start at the lowest degree, which is x to the 0, and then go up to the x's to the 1s. So I could call this b a0, I could call this m a1. Now, for the function f of x equals e to the x, because that's what we've been asked to do for the function e to the x, we're asked to find a first degree polynomial. Okay, so we have our p1 of x equals a0 plus a1 of x. And we want the value and the slope to agree with the value and the slope of f at x equals 0. Now, I don't know that they actually have examples of this in the textbook. There we go. Yeah, number 5. Okay, 5 through 8. Find a first degree polynomial P1 whose value and slope agree with the value and slope of the function f of x at x equals c. Okay? All right, so, so we want to do it near 0, right? That's what it said, at a point near 0. So we want p of 0 to equal f of 0. Well, our f of x is e to the x. And our p of 0 is a0 plus a1 times 0. So f of 0 is e to the 0, which is 1. P of 0, since this is our p of x, a0 plus a1x, is a0 plus a1 times 0, because we're doing it at x equals 0. And that gives us that a1 is 1. Now we also want not just the values to agree, but we want the slopes to agree as well. We'd like f prime of 0 to have the same slope as p prime of 0. Well, if f of x is e to the x, the derivative of it is e to the x. We're going to replace x by 0. We'll get e to the 0, which is 1. But we want that to equal p prime of 0. Now, if we go back to what p of x was, it was a0 plus a1x. If I take the derivative of that, the derivative of constant is 0, and the derivative of a1x is a1. So what happens is I need p of 0 to equal p prime of 0 to equal f prime of 0. F prime of 0, of course, we established is 1. And p prime of 0, because there's no x over here, is just this a1. So a1 has to equal 1, a0 had to equal 1, and therefore we replace the a0 by 1, the a1 by 1, and we find that our tangent line that approximates our curve near that point is the line y equals x plus 1. Okay, note the graphs in P of f of x and P1 of x are pretty much the same near or at x equals 0, i.e. at x equals c. That is, f of x is approximately equal to P1 of x at, which is near or about x equals 0 in this case. Okay, so polynomial approximations of functions, given a function and an x value. Now that x value, they're going to call it c. If c is 0, you're going to have what's called a Maclaurin's polynomial. If c is any number really, it's a Taylor. Even if it is 0, it's still a Taylor polynomial, but if it is 0, it's the special Taylor polynomial called a Maclaurin's polynomial. So you'll be given a function, you'll be given a c, and you'll be asked to find a polynomial of degree n to approximate the function value f of c. So again, the polynomial is either centered at c, expanded about c. So therefore, we're going to need, okay, if it's at 0, which is Maclaurin's, you'll need f of 0 to equal pn of 0. So you want their y coordinates to be the same at x equals 0. Then you want their slopes to be the same, which is the derivatives. Then you want their concavities to be the same, etc. So if we go back to our y equals e to the x, find a polynomial of degree n. So we already did the first one, okay, but let's do the second one now. So it's the same function we had before. So if the second degree polynomial is going to be a0 plus a1x plus a2x squared. That's what makes it a second degree. Well, we already know from our work, which we did before, that a0 is 1 and a1 is 1. That leaves us with plus a2x squared. Now, what we need is we need p2 of 0 equal f of 0, because this question is near 0, near c equals 0. So P2 of 0, well, f of 0 is e to the 0, which is 1. P2 of 0 would be, if we looked at it here, P2 of 0 would be 0 plus A0. So P2 of 0 is A0, therefore A0 has to equal 1, but we already had that. We also need the first derivatives equal to each other at 0. So f prime of x, if f of x is e to the x, f prime of x is e to the x, and f prime of 0 is e to the 0. So again, that's going to be equal to 1. Let me just fix this. Okay. We need f prime of 0, though, to equal p prime of 0. P2 prime of 0. So here's P2. So P2 prime means I'm going to take the derivative of this. Well, the derivative of A0 is 0. The derivative of A1x is A. And the derivative of this term is 2A2x. Okay, so that's P prime, P2 prime of x, but I want to evaluate that at 0, which would be 0 plus A1 plus 0. So I will end up with A1 equals 1. And we already had that as well. But we also need the second derivatives. Well, if this is the first derivative, then the second derivative is going to be 0 plus 2A2. We need the second derivative at 0 for p to equal the second derivative of f of 0. So f of x is e to the x, first derivative is e to the x, second derivative is e to the x. So the second derivative at 0 is e to the 0, which is 1. The second derivative of p2 at 0, since p2 is 2a2 and there's no x to replace by 0, that means 2a2 would have to equal 1, which means a2 would have to be equal to a half. And then you could actually go in and change that. Okay? Oh, this is a long time ago, Michaela's graph.